Okay, so what you actually want to do, and what we'll do in this class, is the effectiveness-NTU solution method. So let's define what these things are first of all. So first, effectiveness. We're going to represent effectiveness using the epsilon symbol. So this is effectiveness. And then NTU here, that's called number of transfer units. Okay. So what do these things mean? Well, effectiveness is basically a measure of how much heat is exchanged from one fluid stream to another compared to some theoretical maximum that you could achieve. So you take your design, you maybe consider what it could theoretically do, and you look at then what it actually does, and that's your effectiveness. The NTU is number of transfer units. That is a non-dimensional way of saying how large your heat exchanger is. So if I have like an NTU of 1, that means that relative to the amount of mass and specific heat, or the capacitance going through it, this is the relative size of the heat exchanger. All right, so 1 would be, let's say, a smaller heat exchanger than like a 5 or something like that. So effectiveness is always going to be in the range of 0 to 1, where number of transfer units is in the range of 0 to potentially infinity. Again, both are dimensionless numbers. All right, so what's this idea of like what the heat exchanger could theoretically do, like its maximum heat exchange. So let's like write some equations that help us decide what that is. So we're looking for some rate of heat exchange that sets the upper limit for a given device called Q dot max. So we can do that by looking at maybe two perspectives. One would be, let's first look at the hot side. So if from the perspective of that could occur in a heat exchanger. Well, it would be if I have the capacitance rate from the hot side, C dot H, that's how much energy the hot side can carry. And then I look at like the maximum temperature difference that the hot side could achieve. Well, that would be the hottest temperature, THN, and then the largest delta T would be if that hot side went all the way down to the TCN, right, the cold inlet temperature. So THN minus TCN. That would be the maximum I could theoretically put into the hot side. So this would be Q dot max comma H. All right, we can do the same thing for the cold side. So Q dot max C is C dot C. Again, like we'd be going from THN, that's the hottest I could ever get the cold side. And then the coldest that the cold side is TCN. Okay, so notice we've got the temperature difference is the same for both of the fluid streams. They're only differing by the capacitance rate. Okay, so once we've decided this, we can maybe consolidate this a little and just say Q dot max in general is equal to, well, something related to C dot H and C dot C. But we have to decide maybe which one of these two is really going to limit the maximum heat transfer rate. So this is kind of a lot going on here, right? But what I want to do is find the maximum overall. The maximum overall heat transfer rate would be either limited by the hot or the cold side. So really I want the minimum of these two things, right? Because that's going to be the upper limit for my device as a whole. So I'm going to take the minimum of C dot H and C dot C and multiply that by the temperature difference, which is the same, THN minus TCN. Okay. We can call this bit over here, this kind of mess, let's call that, let's call that C dot min. So C dot min will correspond to the lower of the two capacitance rates, and we'll just use that symbol moving forward. All right, so from this point, now we have to, we have the tool that we need to maybe define effectiveness a little bit more precisely. Okay, so effectiveness here, we can now say effectiveness is actually equal to the actual heat transfer from one stream to another divided by the maximum, Q dot max. So let's just say Q dot here, this is actual, and this is like the theoretical, or the limit. We can take this and let's substitute in our new definition of Q dot max. So epsilon is equal to Q dot over the maximum, so C dot min times TH minus TC in. All right, and now we've kind of got another step. So eventually what we need to do is actually solve for Q dot, right, the real heat transfer, and then we can relate it to effectiveness. So what about this NTU thing? So NTU, so let me just say this is the non-dimensional size, in quotes, of the heat exchanger. The definition for NTU is NTU is equal to the conductance, UA, over the minimum capacitance rate, C dot min. All right, and again, it's worth like looking at this for a second. So I'm taking some physical size, A. I'm taking some representation of how resistive heat transfer is, that U. Taking the product of those things, so it's like what's on the top is basically like my physical ability to transport heat per unit Kelvin. Right? It's like a watts that you can transmit per unit Kelvin. Divide that physical size by the rate of heat transfer going on the minimum side, or on the minimum, the lowest of the two flows. So if I have a physical size that's the same, UA, and I maybe slow down my flow a little bit, like on both sides, that actually changes the NTU, right? So the NTU is kind of it's dependent on the flow conditions as much as it is like on the physical size of your heat exchanger. All right, so that's NTU. We can then also define something that we need. So another piece of information here. It's called the capacitance. Can I spell capacitance? Ratio. All right, so this is C sub R. C sub R is the ratio of the two capacitance rates, where one is the minimum on top and the other is the maximum on the bottom. All right, so we'd say minimum of C dot H, C dot C, divided by the maximum of C dot H and C dot C. Okay, so again, this is going to be a number between 0 and 1. And why is this useful? Well, because it kind of helps us develop a set of curves for the heat exchanger. So what does it look like, by the way, if I have a capacitance ratio that's not 1? So let's say we plot out temperature as a function of position. So if I have a capacitance ratio, that is the C dots are equal to each other, what does my temperature profile look like in a counterflow heat exchanger? Well, let's say this is the hot stream here. The cold stream is going to be adding heat at exactly the same rate as the hot stream, and the mass flow times specific heat is the same, therefore the delta T's have to be the same too. So like this would be hot. You'd have a cold stream that would look something like this, but they'd have to be exactly parallel to each other. All right, so this is for CR equals 1. What happens when CR is not equal to 1? Well, you have like one flow that, as it's adding heat, it's sort of changing its temperature more quickly, because the only thing that's sort of left to change are the temperatures. So a CR of not 1 might look something like, I don't know, we'll keep the hot the same, but it might look something like this. So this would be CR less than 1. So they're no longer parallel. I'm not sure my first two lines are parallel, but it should be. But you get the idea, right? So like now one of the two fluid streams is changing temperature, and it's doing so more quickly. All right, so all of this now can kind of feed in together to like to give you some kind of relationship between effectiveness, NTU, and heat transfer. All right, so let's go on to the next one here.